Good morning to all. I am Dr. Neel Kamal, Associate Professor, EEE Department, SCT, IIMT University, Meerut. Today I am discussing with electrical machine modules. So this is my first lecture about single phase transformer introduction. So let us start. These are the contents which we will discuss in this lecture: transformer introduction, construction, principle of operation, EMF equation, ideal transformer at no load, practical transformer at no load, on load operation of single phase transformer, equivalent resistance, referred values and equivalent impedance, and equivalent circuit of single phase transformer. So let us start. First of all, what is transformer? Transformer is a static device. It doesn't have any rotating part. What is the use of transformer? Why we are using transformer? Transformer is a static device in which we have to raise or lower down the value of voltages for the transmission and distribution purpose and even domestic purpose also. In this figure we are looking here generating station having, just a minute, 11 kV basic unit of generation. For transmission, by mathematical derivation we can easily prove that as we go higher and higher value of voltage, there will be saving of copper material, there will be better efficiency and better regulation. This is why we use higher value of voltage in transmission purpose. So transformer required. In this figure we are looking here 11 kV the generating value, and then we have raised this up to 440 kV for long transmission distribution. Just like example, suppose we are here in Jammu Kashmir and we have transmit voltage to the Kanyakumari area, or we can say in the Maharashtra area to Calcutta side. So we are having the thousands of kilometers. So we have to raise voltage as high as possible. So in this figure we are raising the voltage up starting from 11 kV to 400 kV line. And after the reaching point we are having to distribute the voltage, and then we have to step down the voltage by using further transformer, that is known as the step down transformer. Again we are getting the 11 kV line, and then by using the star connection we can use 440 volt and even for the domestic purpose 220 volt line. So we can say conversion of electrical power at one alternating voltage and current level to another with little power losses. We have the power losses because as the materialistic characteristics we have the resistance, we have inductance, we have capacitance in material. So there will be naturally losses will occur. So these are the losses very less comparatively, and conversion does not involve any moving part. Transformer doesn't have any moving part. It is purely static device. So we can classify transformer on different manner, just like power transformer basically to transfer the power, distribution transformer to transfer the power on the distribution level, instrument transformer we are using here for measuring and protection purpose, and earthing transformer for earthing purpose, rectifier transformer for providing the controlling supply. In addition to, we can classify as per our phase system, because we have phase system like a single phase system, three phase system we are using. So basically we can say we have two type of transformer, single phase type transformer and three phase type transformer. Simply we can say based upon the number of winding, single winding transformer, two winding transformer and three winding transformer. As per the voltages, these are the abbreviations: LT, ST, EST, UST. LT means low tension, ST means high tension, EST means extra high tension, ultra high tension. These are the different level of voltages by which we have give the name LT, ST, EST and UST like. and these are the voltage by which we can say LT means if we have the 650 volt, then it comes under LT line, and from 11 kV to 33 kV we can say high tension line. EST means extra high tension line starting from 66 kV to 400 kV line, and similarly UST very high value of voltage 765 kV onward line. This is the ultra high tension line. So as per the voltage levels we can say there are different type of transformer we are using here, and as per the voltage ratio we can say step up transformer or step down transformer. When we have to raise the level of voltage we can say step up transformer, and when we have to lower down the value of voltage then we can say step down transformer. And as per the insulation we can say dry type transformer, oil immersed transformer, gas filled transformer, as per the insulation required, because there will be the generation of heat. So to reduce the heat and to remove the heat we are having the different type of transformer here named given as dry type, oil immersed and gas filled type. So these are some figures about the construction of transformer. Based upon the construction of core we can say we have the core type transformer and cell type transformer. In core type transformer we are looking here winding. This is the winding part. Just a minute, I am taking the pen part here. This is the winding part here. Winding surround the core part. This is the core part, metallic part, core part, and this is the winding part. So we are looking here in core type transformer the winding surrounding the entire core part, and in cell type transformer this is the shape of cell type transformer. In cell type transformer we are looking here winding is inside inside part. So we can say core wound the entire winding. Physically we are looking here entire core is wound the winding, but in case of core type winding is shown in outermost part, winding in the outermost part, so core is surrounded by the winding. So this is the main difference between these two types. Depending upon the turn ratio we can say step up transformer and step down transformer. We are looking here in step up transformer the number of turns here is somehow greater than as compared to previous case. So it is the step up transformer. Here we are looking here what number of turns in primary side is greater than in secondary, that of secondary side. So it is the step down transformer shape. Based upon the structure of coil we can say we are having air core and open core type. In air core system there is no physically any core inside the winding, but in open core type system there is the ferromagnetic material inside, because we have to use more and more magnetic field to the use in the winding. So that is why ferromagnetic material inside the coil is somehow better in this case. Now how the transformer work, what the basic principle of transformer, how it can easily raise or easily lower down the value of voltage. We can look here, this is the winding known as the secondary winding, where we are applying the supply system. This is known as the primary side, and where we are using the load here, if we are using the load here, this is known as the secondary side. Both side where we are using the primary supply, where we are using the supply system, this is known as primary, and when we are using the load, this is known as the secondary side. Any side can be primary or secondary side. So when we apply supply voltage here, there will be the generation of flux in this core, and flux will not only confined in the primary side but also in the secondary side. This is the secondary side. The flux will go from this primary side to this secondary side, entire flux. And we are using the AC supply here. This is the AC supply, means AC supply means the voltage V is equal to Vm sine omega t, means variable supply. With respect to time, the voltage level will be changed. So flux will also in sinusoidal nature. Similarly, so this flux will also change with respect to the time, and this flux is also going in this side, secondary side. So definitely there will also a change in flux, and whenever the flux change with respect to time, this is known as the induced EMF. So this is simply generation of induced EMF, and this generation will be in both side, in primary side and in secondary side. We can check the value of magnitude induced in the secondary side by using this formula N2 d phi upon dt, where d phi upon dt is the change in flux and N2 is the number of turns in secondary side. And similarly, we can check the value of induced EMF in primary side, N1 and d phi upon dt is the change in flux with respect to time, and by using this we can say E1 upon N1 is equal to E2 upon N2. By using this ratio we can check E1 upon E2 is the N1 upon N2. So this is known as the turn ratio or transformation ratio. So transformation ratio is basically N1 upon N2, and it is equal to V1 upon E1 upon E2. And when we use load in the secondary side, there will be the voltage known as the terminal voltage V2, and similarly the voltage of this side is known as the V1. So definitely this is also equal to V1 upon V2. So all are the same. And one thing, in such case, power rating means multiplication of voltage and current. So power rating means VA remains similar in both sides, means V1 I1, this is the multiplication of voltage and current in primary side, and that is equal to the V1 I1 is equal to V2 I2. So this is the multiplication of primary voltage and primary current, and that is equal to the secondary multiplication of secondary voltage and secondary current. So by this formula we can say V1 upon V2 is equal to I2 upon I1. You are looking here, V1 I1 is equal to V2 I2. So power remains same in the both side, either in primary side and in secondary side. In primary side, that is known as the V1 I1, and in secondary side this is the V2 I2. So we can use this formula like V1 upon V2, and that is equal to I2 upon I1. So all are the same. These are the ratios. This is the current ratio, this is the voltage ratio, this is turn ratio, and this is the ratio of induced EMF in the primary and secondary side. Escape this. All are the same. Now we are having a quiz. Transformer operates on what principle? So transformer operates on the principle of Faraday's law of electromagnetic induction. What is this? Whenever the flux change with respect to time, there will be the generation of induced EMF. This is known as the Faraday's law of electromagnetic induction. Flux change with respect to time is known as the induced EMF generated. For step down transformer, output frequency is in both side, in primary side and in secondary side, frequency remains same. There will be no change in frequency frequency remains same on either side. So in step down transformer, output frequency is same as that of input side. This is the output side. Now it is equal to input side frequency. Third one, transformer works on which type of supply? Transformer works on AC supply. Transformer cannot work on DC supply. We are having two type of supply here. We are having two type of supply. One is DC supply and second is AC supply. Transformer can work only on DC supply. Transformer cannot work on DC supply. Transformer work only AC supply. Why it is so? As we know, in DC supply system there is frequency equal to 0. Frequency is equal to 0 means there will be no change in flux, and whenever there will be no change in flux means there is no induced EMF. Then what the use of transformer? Basically we are using transformer to raise the voltage or to lower down the value of voltage. In this case, when frequency is 0, there will be no induced EMF generation. So we can say on DC supply transformer cannot work. Which one of the core or cell type has 3 limbs? We are having 3 limbs only in cell type of transformer. Yeah. Now, how transformer works on different load? Basically, we have to discuss before it about the ideal transformer. What is ideal transformer? And then we will discuss about practical transformer. Okay, actually practical transformer is the real transformer that actually have. Ideal transformer is just a assumption we are having. Ideal transformer means a transformer which has no loss, its winding has no ohmic resistance and no magnetic leakage, and therefore no I square loss, no core loss. And when we have no loss, no any type of loss, means we are having 100% efficiency, and 100% efficiency is not possible because there will be definitely some losses. Even losses may be as low as possible, but we cannot say that 100% efficiency. So ideal transformer is just a imagination. We can say we are having a transformer that doesn't have any type of loss, and when there is no loss means 100% efficiency. That is practically not possible. But why we are using ideal transformer? Why there is a need of discussion about this? Because by using this system we can easily understand about the practical transformer, how practical transformer can work. So ideal transformer, this is the ideal transformer case in which we are having supply, AC supply here, and then current flow, because this is the closed loop system, so definitely there will be the flow of current in this system, and this current will produce flux inside the core, and with the change of this flux there will be induced EMF, generation of induced EMF. But in case of ideal transformer, we are saying that this is the ideal case, ideal transformer. Ideal transformer means the supply current is totally used in magnetizing of this core, totally. Complete current will use in developing or in generating the magnetic flux. This is the vector diagram. As we know, we are having a supply V1, then this current will produce totally magnetic field, and if we are using the magnetic field, this means current will lagging behind this supply voltage by 90 degree, because it is pure inductive case. Pure inductive case means there is 90% lagging of current with respect to supply. So this we are showing here the flux and magnetizing current in the same direction. But what about E1 and E2? E1 and E2 are the induced EMF, and induced EMF, as the name suggests, induced means these EMF always oppose the cause by which they are generated, and the cause of the generation is simply V1. So that is why E1 and E2 are just at 180 of V1. So this is the vector diagram about the ideal transformer, in which we are looking here entire current, that is known as the magnetizing current, used to develop this flux, and this is entire flux. There is no leakage flux, totally flux is in the core side. Next, practical transformer at no load. Practical transformer at no load means we are having a transformer that have no load on this secondary side. No load on this secondary side means this secondary side is opened. This secondary side, just a minute, open circuit means there is no current in this side, only voltage exists but there is no current at this side, and whenever there is no current in this secondary side means there will be no losses on this secondary side. And this is the primary side. We are using the AC supply system here. We are having the AC supply here, AC supply. Then this is the current. That current is known as the no load current, because there is no load at the secondary side. Then we are saying it no load current in the primary side, because there is no current in secondary side. So this will develop the flux inside the core, and where we are using the supply system, this is known as the primary side, and whenever we use the load, this side is known as the secondary side. But in fact we are having no load at this slide. This is the vector diagram about the no load current. No load current will basically divide in two different parts. One is known as the magnetizing component, and secondary is known as the wattful component. This is magnetizing component, this is wattful component. Actually every vector have two component if we resolve in horizontal and vertical component. So this is the horizontal component, because this is the power angle between voltage and flux. So we are having this side magnetizing component of current, and because this is the purely inductive by nature, in the previous slide we already have seen here, and this is the wattful, or we can say active component. Why we are saying it active component or wattful component? Because it have resistance, and this resistance will produce loss, that is the resistive loss, resistance loss. That is why we are saying is wattful current or active current, or we can say true components. We are having the different names here. So I0 is the no load current that can resolve in two different parts. One is known as the magnetizing component, and secondary known as the no load component. And this no load current is divided in two different parts. So definitely we can say only in the parallel system is possible, because we cannot show these in the series system. We are dividing this current, no load current, in two different parts. One is the horizontal component and second is the vertical component. So this is the magnetizing component and this is the horizontal component. So core loss resistance, the value of resistance by which heat will observe, that is the R0 is V1 upon IW, where V1 is the supply voltage and IW is the wattful component, and magnetizing reactance XM by which the totally flux will produce, this will be equal to V1 upon IM. Equivalent resistance of transformer. Why there is a requirement of equivalent circuit here? We know in case of two winding transformer, we have two different winding. One is known as the primary side winding and second is the secondary side winding. These windings are not electrically connected. These are electrically isolated totally. There will be no electrical connection between them. Then to make calculation easy, it is possible to shift entire resistance of secondary side to the primary side or entire resistance of primary winding in the secondary side. So we are saying this word referred to primary side or referred to secondary side. So equivalent resistance of transformers means the resistance of two windings that can transfer to any one side, and it is done in order to make calculation easier. As we know, if we are having two resistance, suppose that R1 and R2, so if we connect these two resistance in series, we can say total resistance will be equal to R1 plus R2. But that is the case only when we are connecting these two. But in such case, when there is electrically isolation, this is the electrically isolation, this is the electrically isolation. So resistance of primary side and resistance of secondary side is not connected overall, but for the calculation purpose, to know what is the overall impact of this resistance, we have to shift this side resistance to this side or this side of resistance to this side. So this is the example. Suppose that R1 and this resistance, secondary side resistance, if we shift in the primary side, transfer to primary side, then we are having the name now R2 dash. R2 dash means R2 upon K square. What is K here? K is the turn ratio. K is the turn ratio. So R2 upon K square is the value of resistance, secondary resistance, when it is shifted in the primary side. So overall we can say R01 equivalent resistance in primary is equal to R1 plus R2 dash. This resistance is now shifted here in the primary side in this figure, and we are having the value R1 plus R2 dash. And similar case, when we shift the primary resistance to the secondary side, that is known as the referred to secondary side. R1 is the resistance of primary side and R2 is the resistance of secondary side, and when we shift this resistance toward this side, then the value, effective value, will be equal to K square R1 plus R2. R1 dash plus R2, and the value of R1 dash is equal to K square R1. And again I am saying what is the value of K? K is equal to the turn ratio. So this is the equivalent circuit of transformer. R1 is the primary resistance, X1 is the inductive reactance, and this is the primary current, and then this no load current component have the two different part here, active component or wattful component here, and this is the magnetizing component. So active component in the resisting branch, R0 is shown the resistance of this active component, and magnetizing component have the equivalent reactive value X0, magnetizing reactance, inductive reactance. And this is the secondary component of current here. E1 and E2 are the primary induced EMF and secondary induced EMF, having the turn ratio N1 and N2. Then in the secondary side, current will be I2 and effective resistance is R2, and X2 is the inductive resistance of secondary side. And load is attached here in the secondary side. This is the load component here. Exact equivalent transformer as referred to primary side. What is the meaning of exact resistance? Exact resistance means when for the calculation purpose we have shifted the values or the parameters of this transformer to either side. Just like in this case we are referring this to the primary side. The total value of secondary side is now on the primary side. So in this case we are looking here. This is the primary components. So these are simply R1, X1, overall impedance Z1 we can say, and I0 is the no load current having two different part, no load component, active component and magnetizing component, and secondary side resistance and other values are now shifted in the primary side, refer to the primary side. So this is the R2 dash and this is X2 dash, overall impedance will be Z2 dash. And similarly secondary voltage is now V2 dash. Dash means now these are referred in the primary side, and the load ZL dash is equal to ZL upon K square. When we are shifting all secondary values to the primary side, we have to divide all resistive value by K square, and in terms of current or voltage we have to divide it by K. So these are the values like R01 is the equivalent primary resistance is equal to R1 plus R2 dash here, where R1 is the primary side resistance and R2 dash is the resistance that is shifted in the primary side, and after this shifting this value is R2 upon K square. And similarly in the inductive reactance case, X01 is equal to X1 plus X2 dash, where X2 dash is the value having the value X2 upon K square, and overall impedance of these R01 square plus X01 square and then under root, and it is equal to, this is the overall value. Thank you. And now in the next lecture we will discuss about the voltage regulation, transformer efficiency, different type of losses here. Thank you very much.